Okay, sorry for the interruption. Yeah. So, okay, what we did is we created, this was our first step, choosing your tiling, and this is the generation method that is going to be applied. This is fairly simple pattern. There is nothing fancy about it. There is not an interpolation or heterogeneous event happening. This is the most easiest thing that you can do. So at this point, we can start to know our modification methods. Okay. As I stated, there are 4 modification methods you can apply either at the end of your tiling generation or at the end of your pattern generation. Let's start with a simple one. This is the what we call mirror subdivision component or mirrored subdivide quad. What basically is done here is we take each cell and we divide it into 4 subcells, 4 smaller ones. But the good thing about this is, as you can see on the icon for the component, the order of the point in each subcell or in each new tile is different in a way that instead of let me flatten this input. Instead of giving the old classic rectangular grid, if I plug this one in, you can see that the pattern has 1 horizontal and 1 vertical mirror axis, right? So this can add some complexity to the pattern that we had. There's also a Boolean button here. You can change the state to manipulate this mirroring behavior. If you plug false, that mirroring behavior is not happening, and if you change it to true, that mirroring thing is happening. So this is an example of adding a modification at the end of the tiling part. So at this point, it's fairly easy that we can change our generation method. In order to find out which generation you would like to use, I suggest that you always use Parakeet, always use Grasshopper in the draw icon mode. In your draw icon mode, because by taking a quick look at the icon, you can find out what happens in that. So let me, instead of this one, let's select another genotype. Maybe we can turn off the preview for the grid. And and if we want to use this guy as well, here's the resulting pattern. I just realized that there might be a lag or a small latency in my connection, so I'll try to move parameters more slowly. So at this point, can someone give me a feedback that I'm talking too fast or? Okay. So I assume students are already familiar with the basic concepts of Grasshopper, right?
Some of them are, not all, but some of them.
Okay, so let me mention again that if you have any question, you can type in the chat box of the Zoom, and Esmaeil can take the answers. So what we did so far is creating a tiling and then simply connecting the tiling to the generation method. Okay. So at this point, let's take a look at some of the more complex tilings that we have in Parakeet. We have tried to be as clear as possible in the components description. So, for example, this is a tiling of, as you can see, there's a part in the bracket specifying the valencies of the points in this polygon. So, for example, this is a 3, 4, 6, 4 tiling. They may have other names, but I don't want to go into too much technical data. This is basically a combination of the way we created this tilings is they all have the same inputs as an ordinary tiling from Grasshopper. So all of them ask you to specify the number of tilings you want in X and Y direction and the plane that you are going to use for the tiling. So here's, for example, a more complex tiling, or this one. And of course, you can combine these tilings with any pattern generation methods you like. This is actually one of my favorite ones because it creates some pentagonal tilings. And all of them, if they have parameters, they are either asking for angles or some linear parameters. It's best to always give them numbers from 0 to 1, but some of them work with numbers higher than that. Okay. Is it too fast now, Esmaeil, or? Okay. Okay, sure. Okay, let's create a more advanced pattern with what we have learned so far. So we have a simple grid, rectangular grid, and we want to create a deformation parquet or a heterogeneous transformation. We can do this with any of our generation methods, right? For example, let's use the K1 again. We saw that if we just plug in our tiling to the genotype, because they are all working with the same factor, they are all associated with the same number, so we see the same behavior in every point, in every part of the pattern. So what I have to do is I need to create different numbers for each cell. I mean, for each of my base grid cell, I have to find a new number, a unique, a different number. A simple way to do that is, for example, using the X, Y, or Z coordinates of the cell's midpoint, of the cell's centroid. In order to do that, we are going to get centroid or center of each cell, which is fairly an easy task. You can use it. You can use area components to get the centroid or polygon center. This one, okay. And we need to get the, for example, the x coordinate of this point. I mean, actually, if you look at the C output, it is the coordinates of each point. At this point, I'm going to need the x coordinate, so I'm using a deconstruct component to get the x coordinate. And just to show you what happens if you plug in x, it won't create a beautiful pattern, but it will get you a notion of what we are trying to do. Is you see a pattern that is changing in the x direction. The reason that I'm seeing not well organized pattern is that the x parameter is too high. Okay, so we have to remap it. We have to scale it down to numbers from 1 to 0. In order to do that, we can use a remap component, which basically takes some values. You have to tell it that our initial range is what? I mean, you have to tell them. You have to tell him that my numbers, my initial numbers are between 0 to 11 and half, because we have 12 cells, and you have a target domain, meaning that you specify that I want my numbers to go in this range, in this domain. For that, I'll say that I want my numbers to go from 1 to 0. Okay, so if we connect this, you can see that. Let me again change the color of the tiling and genotype. Okay, so what we did is we created a transforming pattern in the x direction. Of course, let's make a couple of changes. You can we can do this with the y coordinate, and z coordinate is meaningless at the moment because it's a planar. It's a planar tiling. So then let's substitute this one with some of our other methods. For some of them, maybe you can, maybe you need to change the target domain, so so that you can see a more nice looking pattern. For example, right now I gather that I understand that my upper limit is too high because they are rotating. They have rotated too much, so I lower my upper limit. So, okay, here's we have. So, and we can of course do the same with another tiling, because we have just we are new to tiling. I always try to show you a number of different ones. That is the same logic applied on another tiling. Okay. So, if there are not, if there's no questions so far, we can continue to make other things. Any questions? Okay, so let's take a step backward and take a look again at what we have learned so far. We have our first choice is selecting a tiling method, right? And then we had a couple of modifications that can be applied on that. So let's slowly talk about some of these modifications. We talked about one of them, which was this one, mirrored subdivision, which basically divides cells into quad subcells and manages the order of the points to create a mirroring effect. Let's talk about another one, which is the truncation method. Let me find that. Loop truncate, yeah. Okay. Truncation means that if you have a cell, you start to making your cells smaller and smaller. You start to move from each vertex towards the midpoint of each cell. So after doing some truncation, you will end up with a cell like this. If you continue to do the truncation, you get a cell like this, okay? And the truncation 0 is basically just exactly looks like the same pattern that you have inputted. So truncation means let's actually say this in a simple grid. In 3D, truncation is usually called Archimedean solids. I'll show you the examples of the 3D space. Okay, so as I try to explain, when you truncate a pattern, you start to gradually move your vertices towards their midpoints. So always for this particular component, you have to flatten the input, so all of them are analyzed together. For the D parameter, you give a number between 0 and 1, which is the amount of truncation. 1 is actually right in the midpoint, right? And there's another option to do this process recursively. I mean, do this process one more time. So if you plug in, for example, 2 in the iteration input, this process is done 2 times. Okay, this is the result after the first truncation, and if we truncate it again, this is the second result, third, and so forth. But I would suggest that because you recursively are getting smaller and smaller, don't do this more than 6 or 7 times, or it will possibly crash Rhino. Okay, so back to the question that why are we doing this? We are doing this to create a new tiling so that we can apply our genotypes on. Okay, this was our tiling before truncation. Excuse me. And when we add the genotype, for example, this one, this is what we get before the truncation, and this is what we get after truncation, because we have so much more cells, so there's a lot of details in this. Of course, the truncation can also be done parametrically. I mean, the d parameter, just as the example I showed about using x coordinate or y coordinate, the d parameter can also be a changing or a unique number for each cell. Okay, so this is the second modification that we learned. It is called truncation. This also, just a quick thing, this also works on 3D objects. So if you have a shape like this, hopefully it would work on that as well. Let me find the one with the curve output, for example, this one. As you can see, the truncation works on 3D geometries as well. And you can also put some of the genotypes on a 3D grid like this as well. Not all of them, because some of them depend on finding out linear intersections, but some of them would also work on a geometry like this. So, back to our tilings. The next one can be the complex transformation component. This component uses a transformation, with complex numbers. Showing what it means is fairly easier to explain. You need to specify a power number, which is basically a number that I would suggest that range from -2 to +2. For example, let me create a number between -2 and 2. So the transformation works like this. It bends and twists the given. Let me just try to slowly change it. Some of the patterns work with negative numbers, and some of them don't. So let me slightly move this further from the 0, 0, 0 origin point. If this is our initial grid, after some complex transformation, we get patterns like this, grids like this. It will actually look better with more complex genotypes, tilings, excuse me. So the point is, instead of working with the classic square grid, you can use the twisted one. This is a affine transformation, meaning that the edges that were collinear before will not stay collinear. They will eventually have collision. So basically you can create some patterns on the twisted version as well. Let us quickly do another one, like this one, Esmaeil. Like, for example, this one. Okay, and here's the complex transformation component. So let's move to the last modification that we can do, and that is creating a dual graph of the basic tiling. Let's have a tiling. Let's have a simple tiling. I'll plug in a exploit component to turn off the preview. Okay. The dual graph is basically a graph which, this is the component for dual graph. I suggest you flatten the input for this one as well. Creating a dual means creating a new network that its points are located in the centroid of the initial cells. So wherever we had a cell, we have a new point for our dual graph, and each two cells that were neighbors before, they are connected by a line. So for example, this one and this one were adjacent, were connected topologically, so we can see a line connecting the centroid of this cell and the centroid of this cell. This is a whole new grid, so you can do a lot of things that we did with this one. We can do this with this one. We can connect them to genotypes and I'm going to move towards making more complex things. If there is any question at this point, I'll be happy to answer. Okay, nothing. Should we go on?
Yes.
Okay. Okay, so let's create a pattern which is not interpolated in a linear way. So let's select our tiling. I don't know, for example, this one. In our previous examples, what we did was creating a pattern based on x or y coordinate, right? Let's create a pattern based on a particular point in space. For example, the midpoint of this tiling. So in order to create that, let's remember that we can, for example, if we are we want to use, I don't know, this guy. The reason that I cannot see any gradual transformation is that they are all working with the same factor, right? So what I need to do is I need to provide a unique number for each cell. In order to create that, again, I can get the center points of each cell. Then I can calculate the distance between these center points to some arbitrary geometry. Okay, for example, let me add 2 points and reference them into Grasshopper. So so what I need is I need to calculate the distance between each of these points in red, to my green points, right? The component that does this task is called pool points. The D, the output D, is the distances that I need to create my pattern. They are a unique number because each cell's distance is unique, so I have unique number for each cell. Again, if I connect it directly to the genotype, it will show something, but it is probably going outside of the box, or it's not a pretty pattern. So I have to again check my numbers. They are too low or they are too high. Again, we use a remap component along with the bounds component to remap our numbers to make our numbers smaller. For example, from a really small number to, let's say, slightly over 1. So here's our resulting pattern. Of course, it's attracted towards these 2 points. It's sensitive towards these 2 points. Of course, you can change them with some arbitrary curve or anything. Now it's responding to this curve. Yeah.
Where the line is, where your curve is,
The,
the pattern seems to be a little bit too overlapping.
they're actually really getting close to each other, but because this is not exactly 0, they are not completely collapsed. If we change it to 0 at the exact intersection, because, for example, for this cell, there's still the distance is not 0. Actually, it's a really small number. So if actually it gets 0 somewhere, there's somewhere in this pattern that the 2 lines are completely over each other.
But can you give them like also a starting number where the pattern still looks nice, because where it's almost overlapping, it doesn't look nice. Start at 0 point.
So you mean that coming up with this, you mean that,
A bit bigger.
sure.
Yes.
Nick.
Yeah, that's what I meant.
Okay, so let me just, these are complex ones. Let us just try something else. Esmaeil has a suggestion to go for the P genotype. Okay, so for the FR parameter, we can use our distance. But we still have to modify them. Okay. So it is moving from a polygon cell into a more curved one. Maybe we're looking at too much cell. Hmm? Okay. And so, and just one more quick thing. If you wish to not use any of these static geometries, there's a mouse component, I believe, in Parakeet, yeah. And if you connect Boolean toggle, it will retrieve the location of your mouse as a as as a point in your active C plane. So if you connect this, you can see that I don't know how fast I'm moving. Let me. Okay. So as you can see, the pattern is actually responding to the position of the mouse. There is also, for example, all of our tilings that we have seen so far, they propagate in a linear way. I mean, you choose number of cells you want in X direction, and they start to grow in the X direction and in Y direction. But there are other types of tilings that they grow in a polar way, or they grow in a substitutional way. That means that they divide in themselves and they get smaller and smaller. We have a couple of these patterns. For example, this one in the is the Penrose tiling. Um, you can select the number of cells you like. This is actually in working with the Penrose tiling, you have to pay attention to one small thing. Um, in the output parameter, of the component, each cell has divided into two polylines. I mean, this is a polyline, and this is another polyline. So in the output, they are actually not joined together. If you want to create a cell comprising all of them, I mean, if you want to have a cell that has a geometry like this, you can use either the mesh from line component. It is actually from the plugin Weaverbird, and plug all the lines to this. This is not actually working. In order it to work, is you have to explode the curves first, because we need all of them as singular lines, not as joint polylines. We have to remove the duplicate lines, and then if you create you can create a mesh with all of them. So you can apply the genotype on each face of the mesh. In order to get faces of the mesh, you can use the face boundary component. This is the genotype K on a Penrose tiling. We were talking about the Penrose tiling, and let's mention the hyperbolic tiling. This is actually what you can look up Poincaré disk. So this is basically a tiling that moves from the center. The center is the biggest cell, and as you move towards the boundary of the circle, your cells get smaller and smaller. You can put various genotypes on that as well. Some of the, because at the moment they are actually curves, and most of the genotypes are working with polylines. You have to do a polyline version of these cells. For example, you can use the discontinuity component to get vertices for each cell, and you connect them with the polyline component, so you have a polyline version of the curved cells, and when you close them, you have this type of grid, and you can use it with any genotype that you like. Yeah.
See that you also have Azure patterns.
Right.
Can they be integrated in the Poincaré as well?
At the moment, the components are coded in a way that they create their own grid internally. I mean, when you put Azure components, they create their own grid. For example, they create hexagonal patterns. They're not working like genotypes that can be applied separately. So at the moment, yeah. But if you like, I can quickly introduce the Azure patterns as well.
Oh yes.
Okay. So the way that these components work is basically you have to provide a base curve for them. So you can create an arbitrary curve on Rhino, any shape you like, but just make sure it's an open shape, not a closed one. Okay, and as you can see, this curve, let me make it smaller. This curve has been applied on each edge in a way that creates a holistic pattern, yeah. But for a more complex version, you can introduce multiple curves. For example, if you
In this case, you can use
Exactly. Exactly. For example, in this one, the component works with one or two as well, but for the best result, we suggest that you use all the three curves. For example, this is our first one. For the second one, I use a polyline, and for the last one, just a simple line. We can reference all of them in Grasshopper. And the resulting pattern is created. This is our curve of degree 1. This is our polycurve, and this is the line. This is the third line. So, and this component has a point that can somehow create a parametric effect. Before that, let me increase the x and y parameters. If you put a point on the MP parameter, it's not going to work at the moment. We still need to change one more thing. What we need to change is this point indicates that indicates the interpolation behavior. But we actually we don't have any interpolation yet. We have to add another input. For example, we want to state that I want this curve to be gradually converted to this one, okay? And I want this one gradually be converted to this one, and I want this curve gradually convert to this one, okay? For example, I have to let me these two in this parameter, these two in another curve param, and these two in another param. So if I connect now more than one curve to each curve input, then my MP defining a point is has a meaning, because you can see that when you get close to the point, you still see the line, and far from the point you see that the line has been transferred to a so, and in order to amplify this effect, we can, let me radically move some control points so you can make the effect more clearly. Okay.
These are Parquet Deformations, actually.
Right, yeah. So let me, I guess, I can show a couple of quick things very quickly, and then we can answer questions if anyone has a question. So, um, um, a thing that we believe is fairly intriguing is, for example, if we have a tiling like this, there are some genotypes that right after you use them, for example, let me show you what I mean. For example, when we add this genotype B, it's a curved one, but as you can see that it looks like that somehow all the patterns are oriented in the same way, right? They are all pointing upwards. This is because the start point of each cell is actually at the same point, right? For example, all of them are starting from their lower left cell point. Sorry. In order to change that, you can use another component in here called random seam. This randomly changes the starting point for each cell. So after using this, you will have so much better looking pattern. It's simply because we have randomly changed the starting point for each cell. And there's a seed input. So if you put a random integer number, it will do this procedure in another way. So I guess for one session, I don't want to get too much. I don't want it to get too much complicated. If you have any question, I can answer them for now.